let me say something more about the Frenet stability problem, which we have looked at last time. So we have looked at the problem of having a prescribed curvature telling us how the curve curves at time t, and then wondering whether this is stable or not. And we have seen there is a resonance situation. If this is not satisfied, we have stability, and if we have resonance, then we are going to infinity. In 3 dimensions it's harder. I just, with some pain, constructed an example where we have instability. So we, in the case when the torsion is periodically changed and the curvature is constant. But of course you can change both the curvature and the torsion, and then it's absolutely not clear what happens in general. So we expect to have, you know, subtle conditions which give us stability. So stability, I mentioned that last time, kind of just as a motivation, is a very important problem in mathematics and mechanics. You are driving something periodically, and you want to know whether the process stays stable or not. So this is a pendulum, and you drive it periodically, and you ask yourself, what happens? Does it become arbitrarily fast or not? Or does the velocity stay bounded? It's a beautiful problem. And last week I also looked a little bit at the discrete version. There's a discrete version of this where you don't, you know, prescribe the curvature at a time, but you just drive for a while, for a fixed time, and then you turn, and then you drive for a fixed time, and then you turn, and you drive for a fixed time, and you turn, and every time you turn the wheel by maybe some constant alpha k, some kind of the analog of the curvature. We have seen the turn is in the discrete case. 136 we have seen in the course that turning is actually the analog of curvature. So we prescribe, we actually every time just change the angle by some alpha, make it larger, and then this gives us a sum, right? Because we add up all these linear changes, so we get a quadratic term, which is equivalent to Gauss sum. So it's something in number theory which is interesting. But it can also be seen as a problem in dynamical system where we have Birkhoff sums which are highly correlated, right? This doesn't produce a stochastic process which is with independent random variables, but these random variables are highly correlated, almost periodically correlated. Now the Curlicue problem can also be generalized, like here we change the curvature. For constant curvature is actually less difficult. Constant curvature is quite an interesting story in general. You know, you have a Lie group and you have a constant element in the Lie algebra, and then what happens is you actually have a path in that Lie group which produces you a abelian subgroup, and so it has to be part of a maximal torus in the Lie group. In SOM, for example, we have just half of the dimensions. So in SO4 it would be 2 dimensions, SO3 it's 1 dimension, SO2 it's also 1 dimension. So we have, depending on the dimension, we have here kind of just a situation which, in the case of constant curvature, can be understood. Constant curvature in the Curlicue case is hard, depends on the, you know, Diophantine properties or, you know, arithmetic properties of this constant. Like for the golden mean, you get the self-similar fractal. It has been studied. Now, in general, when we look at the Curlicue problem in general, when you are changing the curvature, also maybe in a periodic way, this has not been studied at all. I don't know what is happening there, but in principle it's a very similar problem to the problem here, and you can also look at it in higher dimensions where you add up rotation matrices. So what you do is you fly for some constant, then you turn by some prescribed way, and then you drive again, and then you turn again. And this turn can be done you know, in the group of SON. So that's kind of more general here, even in an arbitrary Lie group. Now, we can also do that on manifolds, and that brings us then something to what we do in the 136 next week. We are talking about geodesics, but you can also look here at the problem, both the Frenet stability problem or the Curlicue problem. You can look at it also on manifolds, because locally you are kind of in a Euclidean situation, and so we have curvatures which are geodesic curvatures, and then you have also geodesics. And both cases, the Frenet problem, you know, the question would be, of course, does the curve cover the whole manifold densely or not? And in the Curlicue problem also, you can ask, does the Curlicue actually cover the whole manifold or not? And that is even in the simplest case, you know, also constant case would be something difficult to answer. But it's a nice playground for stability problems. Let me stop it here.